adapter traffic is usually divided in the time slot in 4 different subslots. Basically, you don't need the full rate of 64 kilobits, so you divide it in 4 subslots with 16 kilobits each. This division is very simple. You take the first 2 bits for the first subslot, the next 2 bits for the second, and so on. This stream is then the stream does not have any synchronization marks. You just have this data stream and you have search for the synchronization by yourself. You don't see speeches starting, speeches ending. You have this data stream and you look for it in the packages for where the package starts and where the packet ends. And then you have this package with, in GSM is encoded, which holds 20 milliseconds of speech. This 20 milliseconds of speech is repeated with 50 hertz frequency, so you get a continuous stream of single packages of compressed speech. In GSM, speech is compressed using several codecs. The most common ones are full rate and half rate. Full rate is 16 kilobits, and half rate is, as it says, the half one, 8 kilobits. And we have also several newer and better codecs. For example, there is the enhanced speech codec, but in our case we only talk about the full rate codec because this is what we have implemented so far and which is also supported by our base station. For the full rate codec you find open source decoder, and you can use it to decode and encode GSM full rate speech packages. You just take an audio file, put it in, let it run through the encoder and get the compressed files. But these compressed speech packages are not the packages which are transferred on the ISDN layer. Basically because those packages don't contain the synchronization framing. If you send them, you can't find out where a package starts and where it ends. So they are put in so-called TRAU frames. TRAU is actually the unit, the transcoder and rate adaptation unit, which sits in the GSM network and which takes care of transferring speech into, for example, ISDN speech, which is then transferred to the local, to the Earth-based network. And those TRAU packages contain a header which allows to synchronize them. This header is a specific bit pattern which is only used in the header, and so it can be easily detected. Basically, this this adds some overhead, but the overhead is not too large. We start with 30 kilobit, which we get 13 kilobits per second, which we get from the GSM decoder, and we end with 16 kilobit after putting them in those TRAU frames.
Okay. Yeah. So, as Dieter indicated, there are the actual signaling packets, and there's the radio subsystem layer, which contains messages for radio link layer, dedicated channel, common channel, and transceiver management. What we're going to focus on is the radio link layer, because the radio link layer in turn contains the messages for call control, so that's the actual Q931 derivative that does the call setup, call proceeding, alerting, and so on, indications like in ISDN. There's mobility management, which is for actually like roaming, knowing where a mobile handset is, registration, handover, and so on. This radio resource, which is, as the name indicates, about radio resource management, and short message is a separate layer. Those are mostly specified in GSM specification 04.08. I think that's about 1,000 pages, so it's not all that much in GSM terms. The system that we have right here is a Siemens BS11 Micro BTS, and that Dieter is going to cover a couple of slides about that one.
Okay. Harald already told you that this is a Siemens-based transceiver station. It is originally manufactured by an Italian company. It is manufactured for Siemens, It supports, basically it supports the old GSM 2G network. This means voice calls. It might support data calls in very, in some previous specification before GPRS, but we have not yet tried that out. So it might be possible, but till now we are 100% sure that it works for voice calls, but we don't know anything if we can support data calls in the future. The interesting thing for the base station transceiver is that you can set up the power which it uses on the output. There are 4 stages between 13 milliwatt and 2 watt, and you can choose which stage it uses. So even if you should not try it at home, if you try it, turn it down to 30 milliwatt, then probably you don't disturb too many people. You should not use the 2 watt because this is the power similar to your phone, so you will have a really huge range. The antenna is a directional antenna, so you usually have a 100, let's say roughly 180 degree transmission direction. But anyway, I would suggest if you try it, even if Harald says, okay, don't try it, then turn it down to 13 milliwatts.
Or even add additional attenuators in the RF path.
Of course, this is the recommended way, but if you don't want to spend the money on the attenuators, you know what to do.
Yeah, we actually, somebody from the team verified the output that actually is only 30 milliwatts. So.
Yeah, we can trust this configuration if it's really set to it. Yes, as it's measured, we have measured it. It's really only 13 milliwatts. Okay, the interface. In our case, to our software, the base station controller, this is going over an ISDN interface, and the base station transceiver has 2 ISDN interfaces. We use one to connect it to our base station controller, and currently the second one is not used, but it could be used to daisy chain several base stations. We have a lot of time slots on our ISDN channel 31, and we only need if we support all the capabilities of the base station, we would only need 3 or 4 time slots at all. So we have several spare ones which we could use for other base stations which are daisy chained over the second ESDN E1 interface. When we started with this project, we got some documentation, but this documentation is under NDA. But this documentation, actually, it's not details about how the protocol works, or it's not even details about the hardware looks. Basically, it's something like how to mount the station on the outside, how to make sure that it's waterproofed, how the intrusion detection works, so if someone tries to mount it off the wall, what happens, and such things. So it's not really documentation which is very useful if you want to develop software for this device. So as we said, it's under NDA, we cannot give it, we cannot forward it or put it in the public, but anyway, it's not that interesting to have it because really it's about mounting and such things. And you find most of the specification of how this device works, you will find in the GSM specs actually. When we started with exploring the capabilities of the base station, we were not really aware that all the specification of the protocol is available. The reason is that the ABIS protocol for configuring the base station. Configuring means in this case setting it up. Telling the base station what frequency it should use, what time slot it should use, and such things. This is not the messages you need to communicate with the mobile, but you needed to set it up that it initially starts up. We thought that this messages and this protocol is really specific to the manufacturer of the base station. This was the case, I think, for base stations built before, probably the late 90s. But then GSM introduced a specification which clearly defines how this setup procedure works. And our base station, luckily, really conforms, let's say, 99% to this specification. So we can look it up and see what we can do with it. And this is also a big advantage because in the NDA docs we have, there was also no information about how this protocol should work. Basically, an operator who buys such a base station does not need this information. He, of course, buys the software from the same supplier for his base station controller, and so he does not care what's going on the line. The base station, additionally to this ABIS interface, which is going over the ISDN line, it also has a serial port. The serial port is connected to a program which is also under NDA, which is called LMT for Local Maintenance Terminal. The software basically is used for the service people in the field. They can plug it into the base station, they can check certain settings and adjust some of the settings. But most things of those settings can also be sent over the ABIS interface and is available in the specification. So this program is not that very useful. If you don't have it, it does not care that much. There are a few commands which are interesting. For example, the commands to set up the output power of the base station, and we will provide this information of how to send a few bytes and get back a response from the base station in the wiki. So if someone wants to use the few important commands, all of them will be provided, of course.
Okay, we have to speed up a bit, so let's just go quickly through the couple of pictures.
Okay, here is one of the pictures of the interiors. It's really tricky to get inside. We will provide the information of how to get inside because this is a unit which is used for outdoor usage, and it's really very well closed. So, but when you open it, you can basically see the power supplies, two power supplies, because we have two separate transmitters in this unit. One transmitter can have 8 time slots, and we have 2 of them. There are the filters and the low noise block, which is connected to the antenna. There is the baseband part. The baseband part is basically processing the digital streams which were already demodulated, or which process the data which have to be demodulated, which have to be modulated and later transmitted by the system. We have several huge parts in the left, which are the transmitter and receiver. You only see this large block, but actually they are stacked. There are 4 boards stacked over, and they contain those information. You can see it here on the next picture. That we have several levels. The layers are stacked, and the interesting thing, this is really handmade work. There are a lot of metal is inside. Metal is basically, in this case, used for thermal transmission of all the heat which is produced inside. This base station was manufactured about 10 years ago, and we don't have one single microcontroller which can do a lot of things. No, we have several. We have about 6, 7 microcontrollers, 8 DSPs, and all of them produce a lot of heat. So therefore, there's lots of metal inside.
Yeah, so actually this talk is about how to operate your own heating.
Yeah, and if, as Harald already said, if you touch the base station after it's running for about half an hour or so, I would say in this position where thermal transmission to the air is not that good, we have about 40 degrees on the top. And here in this picture you can see the 2 layers for each of the transceivers in the base station, and each of this layer is divided in a transmitter, in a transceiver, and in a transmitter and in a receiver, and really large PCBs inside. And as I said, every chip is connected to the upper layer with some thermal paste, which dissipates the heat to the upper layer and then finally to the outside case. This is the interface connection. Here we find on the top, we find the connectors to the RF antennas. We have, as I said, we have 2 transceivers, so 4 connectors, 2 antennas for transmitting, 2 antennas for receiving. On the lower part, we have the We have the E1 interface. Those are the coax-like looking connectors. There are two pins inside. It's not the standard BNC connector you might know from old Ethernet, but they contain two. And below